Okay, are we ready? Okay, so welcome back, everyone. Thanks for making it all the way to the end of the afternoon. I'm sure it's been an exhausting day for all of us. Before I start, I want to have a quick show of hands. Who is actually here? So how many people are here from Delft? Yes, I'm also from Delft. That's great. How many people are here from Aachen? Okay, not so bad. But how many people from ETH? That's going to be tough for you. And how many people from Sweden? Okay, very good. So what are we going to do today? So I've been asked, in fact, to talk to you about a particular topic. Namely, I've been asked to talk to you about randomness, entropy, and quantum cryptography. And like when we start with this, so what is our menu? What we're going to do today is I'm going to talk about what is randomness, how we're going to quantify randomness, and how we're going to produce randomness. So today we're going to discover some very important tools that, in fact, anyone who does quantum crypto or quantum information theory should know. They're also quite important if you, say, want to build a device that produces random numbers, and you're going to use them in some experiment, or you're going to build a device or buy a device that produces random numbers, and you want to safely use it in your experiment. Okay. So this is probably what we're going to get to cover today. And tomorrow we're going to produce some very special form of randomness, namely correlated randomness. Randomness is kind of correlated between two parties, which we'll call a key. Okay. So far so good. Maybe before we start, I'm going to ask you, what is a random number? If I'm going to toss this coin, when is the output going to be random? Any takers?
If the coin is not biased.
Okay, very good. So it means it's 50-50. So you were from where? Yes?
Is this a competition?
Are you from Aachen or from Sweden?
No.
Huh?
He's from Aachen, yeah.
Okay. Okay.
It has to be random, it's wrong.
Huh?
Unless it has to be random, it's wrong. I'm from
Okay, very good. Okay, so someone just said there, this coin, if I toss it, it's going to be random if it's unbiased. Okay, so the probability of heads or tails is going to be 50-50. Okay, this I guess what we would all say. Okay, and this is indeed true. This is the one requirement to produce kind of a random bit. So I have a coin here. Actually, it's an Australian coin. So on one side it has like a clover leaf, and the other side it has a queen. Okay, so if I toss it and I'm kind of produce a random number, and I put it down here. Okay, so in fact I've tossed a queen. Okay, it says queen. I'm going to put it here. I'm not going to touch it again. And I'm going to now toss a second coin. Okay, I have another coin, another Australian coin for some reason. And I'm going to toss it. And if I toss this coin, when is it going to be random? Well, I guess you would again say 50-50. Okay. So let's imagine now that I want to toss two coins. I have some kind of crypto algorithm, okay? And I'm going to kind of produce a key that I will feed in this crypto algorithm. Okay, I want to have perfect randomness. Now I'm going to toss my coin here. And I have produced a random number, namely the one that I have in my hand. And the other one that I'm going to use is the one which is lying on this table over here. Okay. So my question to you is, would you say that these two bits that I've just generated are kind of random? I can safely use them now to kind of shield my data from you maybe, or use them in some kind of algorithm. Yes?
If you assume that I'm correlated, sure.
Okay, so if you assume that these two coins are uncorrelated, okay. Yes, they should definitely have this feature, and it's a very good point, because it could be that, I don't know, maybe these coins are entangled. I guess in this case we can be reasonably sure that's not the case. Or maybe, I guess you haven't checked my coin actually. They have the same thing on both sides. Okay, so this is very good. So we want kind of these to be uncorrelated, so they should both be, I guess, 50-50. Okay. So let's imagine that I'm now going to use whatever I have tossed here and whatever is on this table over here to encrypt some information from you. In fact, I'm going to take the answers to the homework exercises, and I'm going to use these 2 bits to encrypt them. Okay. Would you say that the key has been kind of chosen randomly? Does it look random to you? Ah, indeed. Okay, so I turned around. This is not fair. I admit this is not fair. Okay, I'm going to toss it again. And I've tossed it. Okay. So let me ask you this. What is the coin on my table?
So it's random for us, but not random for you.
Okay, it's not random for me. Okay, so this is very good. So the point is here, actually, where are you from? Okay, so this is a very good point, because things may look random for one person, but not for the other. Okay, so me, kind of, I know what is on my coin. Well, I know perfectly what it is. Okay. In fact, if you remembered what is on my coin here that I put on the table, I told you that it was a queen. Okay, so even though this kind of bit is has been random somewhere in the past, you actually know what it is. So in kind of crypto and algorithms, we say that the bit is random if it is 50-50, so it should be unbiased, as pointed out by ETH up there. But it should also have the property that, in fact, you don't have enough information to predict it. Okay? So to you, it looks random. So to make this more precise, so kind of what is a random bit? So let me call my bit x. And in fact, I will use some quantum notation. Okay, so if I say that I'm going to generate a random bit, I'm going to say that, well, with probability half, it should be a 0 state, and with probability half, it should be a 1 state. Okay, so this is really just a maximally mixed state of kind of 1 qubit. So this would be a way to kind of write down kind of a probability distribution, and if I were to kind of measure this, I get 50-50 coin. So the second point is that was correctly pointed out is that it matters kind of whether it's random to whom. Okay? So let's say that I'm going to use this bit to kind of encrypt the message. Then what I want is not just that this is the maximally mixed state, but I want in addition that it is uncorrelated from you. Okay. So we say that kind of something looks random to you if kind of the state of you and the coin that we're going to produce has the property that, well, it's uniform and uncorrelated. Okay. So in this case, kind of, for example, my coin was uniform, but at least if I had kind of used it later, and I told you already what it is, it's certainly not uncorrelated from you. Okay, okay, very good. So the objective, kind of in producing some random number, will be to generate something like this. Okay. So sometimes we don't just want to generate one random bit, but we want to, say, produce an entire string of random bits. And I will always call such a string x, like x1 up to xn. Okay, so if I just write x, I mean the entire string. I will also kind of write the n here sometimes to remind ourselves that actually this is kind of n bits. And in this case, we want that, well, the entire string is kind of uniform and uncorrelated. Okay. So unfortunately, kind of, I guess, as you might imagine, in any kind of actual process or protocol which tries to produce a random number, we can never perfectly succeed. Okay. So this is kind of our utopia. This would be an ideal random number. Okay. So in crypto, people also call this the ideal behavior. This would be my ideal scenario, my utopia that I want to achieve. In any real algorithm, kind of, we can never quite get there. Okay. So what we will kind of produce is necessarily, or usually, not quite of this form, but only almost of this form. So when I say it's almost of this form, we have to think about some measure of what almost means. Okay. So I want to produce a state that is in some sense close to my ideal state that I have here. So can someone suggest some measure of closeness which might be useful for us? Yes? Okay, so the entropy of the distribution. this is a very good one, even though I want something slightly stronger. Other suggestions? Yes?
Maybe the probability of hitting exactly this string that turned out versus the probability of hitting versus 1/2 power the number of bits.
Okay, so when you say the probability of hitting, you mean the probability that I guessed this? Or what do you mean by the hitting probability?
I mean the probability. In the distribution that our physical process actually gets, the probability of getting the string that turns out in the end versus the probability that should be there when
Mhm.
when it runs.
Yeah. Okay, so you kind of want these probabilities to be close, right?
Yes.
So my question to you is kind of how are we going to quantify close? Any other suggestions? Yes? Okay, so the relative entropy. Actually, I like all of these suggestions, even though it's not quite the one that I want to use. Actually, where are you from? Okay. Come on, Delft. Like, I'm disappointed. Okay. Okay. Any other suggestions? Yes?
About probability to actually know this system.
Okay, so probability.
To determine, I'm like opposite of randomness. Probability to know this system, to know the result which you produced.
Okay, so I quite like the suggestion and I want to keep it. Okay, so there's a suggestion over here, namely maybe I want to think about the probability of guessing the entire string. Okay, so I want to keep this here because it will be very useful for us. Okay, actually, where were you from again? Chalmers, yes. Okay. Okay. So one measure of kind of distance that people quite like a lot in kind of crypto or also the generation of randomness is the trace distance. Okay? So what is this trace distance? Okay, so the trace distance between two states in general, and I'm going to apply it to the situation here. Okay? So and I'm going to call this here our ideal state. Okay. So kind of the distance between the actual state that we're going to generate somehow, hopefully, and our ideal state should be small. Okay? And so what is this trace distance? We can write it down as the maximization over all operators M that have this property. So I'll explain this in a second, and let's satisfy this. Okay. Actually, I guess I turned it around. Let me maybe not confuse you. Let me use real ID. Okay. Who has seen this distance before? Very good. Okay. So why is this distance interesting? Okay. So let me maybe tell you kind of what the trace distance operationally tells us. Let's imagine that I challenge you to a game, and I'm specifically addressing the people here in Delft, because I haven't said anything yet. Let's imagine that I'm going to propose to you the following challenge. Either I prepare the ideal state, the stuff that we actually want, okay, with probability half, or I'm going to use the real device. And I challenge you to distinguish between them, okay? So I'm going to send you a state. With probability half, it's kind of the ideal state. With probability half, it's the real state. And you win if you can tell me which one it is. Okay. So if you want to do this, you might make a measurement, okay? So this is the situation, say, I don't know, with probability half, I give you the real state, and with probability half, I give you the ideal state. And the probability that you distinguish between them is you might make a measurement, okay? This measurement has two outcomes, and I'll call them real and ideal, okay? So these are the measurement operators of the measurement that you're going to perform, and if you get this one, like outcome ideal, you're going to say ideal, and if you see this one, you see outcome real, you're going to say real. So the probability that you're going to win my game, okay. So with probability half, I give you the real state. And the probability that you correctly identify it is precisely this, okay? So namely that given that you have this state, you get this measurement outcome. So of course, like you're all very smart, and in fact, after this lecture, you will be even smarter than before, I hope. You might, of course, not use just any measurement, but you might try and find the best one. So let's imagine that I'm going to maximize this over all possible measurements. Okay? I'm going to try and find the best measurement possible. Does someone see maybe how this would be related to this quantity up here? Any ideas?
It's the same one.
Yes, almost. What are you going to do?
Sorry. What I'm going to do with what? If I maximize the P, I get the M, which is string, which is on both, and this is a maximum M, which we use in our definition.
Okay. So let me maybe kind of write this out. Okay. So one thing that I could do is I could rearrange these terms. And remember that kind of if we make a measurement, like these two have to add up to the identity, so I can rewrite this as the identity minus the real state. The measurement outcome for the kind of, that says real. Okay. Okay. So I can rewrite this, and well, what do I get? Okay. So let me maybe do this here, because my space is somewhat limited. Okay, so what I'm going to do is I'm going to rewrite this here as the trace of rho ideal with the identity. Okay. So this is just the trace of rho ideal. And what I have here is minus m of real times rho ideal. Okay. So note that this here is just 1. Okay, the trace of any quantum state is always 1. So what I can do is I can rewrite this as 1. Okay, so this comes from here. And now I have two terms left, and they both involve this term m real. Okay? So what I'm going to do is I'm going to write this as the trace of m real. Okay, so the first term that I have is rho real. And the second term that I have is rho ideal. Does everybody agree with that? Questions? Okay. So of course, like I want to relate this to this distance here, but it's now quite clear how this is going to look like. Okay, if I want to find the optimal measurement operator, so note that they all have to be positive semi-definite, so all of the eigenvalues are positive, okay? Then this m satisfies precisely this condition. Okay. So I can now rewrite this, like if I wanted to maximize this, and I'll write here equality we can be achieved by this maximization. So kind of what I want, kind of if we cannot produce this ideal kind of scenario, I cannot produce some ideal coin, okay, is I want to produce a state such that the trace distance between the ideal and the real scenario is small. And the reason why I want that, and you can kind of see it from this, is because if the trace distance is small, then this gives a very operational kind of meaning, because it means that there exists no measurement that can kind of tell the difference, okay, between the real world and this beautiful ideal world that we're kind of trying to aim at. Okay, so I guess I can erase this. Okay, so the objective will be, if we cannot make this ideal state, our objective will be to in fact produce a state, let me call this rho real xe, that is close to this ideal state for some epsilon. Okay. Where epsilon should preferably be small. So one of the reasons why kind of people who do quantum crypto kind of like this trace distance is because if we manage to kind of produce a random number, like the real scenario, that is close in trace distance, then there exists no physical process that can tell the difference. It also means that if we later use this random number in some algorithm or crypto protocol, then kind of this protocol can also not tell the difference. It behaves almost as if we had used this ideal, beautiful randomness that we really wanted to make. Okay, because any protocol or algorithm that would behave differently if we kind of input the real state instead of this ideal state would of course give us a means to tell the two scenarios apart. Okay? This would be a measurement or a procedure that we can perform to distinguish real and ideal. Okay? So if the trace distance is kind of small, it means that no algorithm and no protocol can see the difference. Okay, so this is kind of why people kind of love this trace distance. Okay. So this will be our objective. We want to produce something that is kind of small. Okay. So let me maybe see how we're getting on. Okay. Okay. So what I want to do now is I want to get back to your suggestion before, because I very much like the suggestion. Okay. And I want to kind of think about the following scenario. In fact, this scenario, I guess, is a very common one. Both in crypto and also in kind of producing a random number. Let's say that I have a process that generates some bits. Okay? Maybe they're somewhat random, maybe not. Okay, we'll investigate this. Okay? So you kind of think that I have a box, and on the top of this box is kind of a button. Okay. And I can press this button, and some number of bits will roll out. So I guess the ideal scenario would be that all of these bits are already perfectly random. Okay? In which case, in fact, one might also say something about the entropy of the string. Okay? So this was a suggestion that kind of came before, namely, maybe I want to look at the entropy of the string. So can someone tell me what is the entropy of a randomly chosen string of n bits? How do I compute it? Yes? Okay, so the entropy is just n. Okay, so why is this so? So the entropy of this distribution P can be written like this. Okay, so I'm going to sum over all the strings. So this means the probability that I choose the string x. Okay. So if the string is perfectly uniform, then this is just 1 over 2 to the n. Which gives me these n. So this is great. Like we all wish that we would have such a box. I push the button and the string comes out and it has entropy n. But let me now ask you the following question. And again, we can kind of play a little game. So like Delft can make up for points. Namely, we're going to play the following game. I'm going to sell you a box. Okay, such a box. You can only use it once. You can push the button on this box, and n bits will come out. Say n is very large, n is 1,000,000. You can use it to kind of feed it into some encryption algorithm to communicate with your friends after you leave. Okay? So my ideal box, in fact, that I will sell you, that has n bits, costs $100. Okay, it's not particularly cheap. Also, unfortunately, like I'm out of these boxes; they're sold out. Okay. But I can sell you another box. And this other box that I'm going to sell you has roughly half n bits of entropy. Okay. I have constructed the box. I know what's going on inside. In fact, I might be trying to read your messages later. Okay. So I've constructed this box, but I make you a promise because I'm not completely unfair. Okay. So I'm going to promise you that, well, it doesn't have n bits of entropy, but it has n half bits of entropy, roughly. Any bits for my box? What are you going to pay for my box? $50. $50? Okay. Okay, this is a good offer. Yeah, sorry. Actually, I have to make another stripe. Okay, so like offer number one for my box is like $50. Seems fair, you know, like half the money, half the entropy. Any other offers?
Do we have any information at all for the first box?
This one?
Yeah, do you give any information?
Yes, so actually for this box, which unfortunately I don't have any of anymore, I promise you that the entropy is precisely n.
Second box, you're allowed to press the button. You're also allowed to press the button only once.
That's right.
How about beats that are, do we know which beats are not, let's say, not random?
Ah, so that's a good question. So you don't know. You don't know, have no idea what's going inside my box?
Random, I don't know. You can somehow select random ones. I will pay 100.
Okay. That's great. Very good. I'm going to sell you my box immediately. Okay. So let me now kind of maybe say one thing that could be going on inside my box. Okay. So I have constructed the box. Maybe I'm slightly malicious because I want to read your messages later. So I actually prepare my box in such a way such that inside my box, with probability half, it will generate, say, 1, 1, 1, 1, 1. And with probability half, it will generate one of the other strings randomly. Okay? So with probability half, it's 1, 1, 1, 1, 1. And with probability half, I pick one of the other strings at random. So I'm not going to do this calculation here because I guess we don't have so much time, unfortunately, together, but I encourage you to kind of do this calculation, and you will find out that the entropy of this distribution, the distribution meaning that P of 1, 1, 1 is a half, and for all the other strings, it's like a half times, well, I pick one of the remaining ones at random. Okay. I claim that this distribution has entropy roughly half. But let me now ask you again. Would you use this box to later encrypt your messages? No? You're shaking your head. Why not?
Because, I mean, probability of getting something that's well known is really wide.
Indeed. So note that with probability half, I will be able to read your message. In fact, with probability half, I will be able to read all your message because I know all the randomness, independent of the length of n. Yes?
I did a beat for $50 because I can buy 2 of them.
Aha. Yes. So this is true. We will investigate this a bit later, how much randomness we might actually get out of 2 of these boxes. But let's get there. Okay. So you kind of said that, in this case, you would not want to use this box to kind of generate some randomness to kind of use in your encryption algorithm because I can guess it with probability half and I can read everything. Okay. So this kind of yes.
In this particular case, if we use the box and an output of 1, 1, 1, 1, 1, then we could be sure that this would not be a string that would be generated randomly. So
that's right. But note that you don't know what's going on inside my box. Okay?
But I know that the complexity of 1, 1, 1, 1, 1 is very low, so that it's very plausible that this is in particular, that in this case the box was not random.
Okay, so because I see everything actually from this stage, I know your strategy. So I'm going to prepare a different box.
And still complexity is
is low.
Probability of any output is low.
You can use random, not random any string to use your, let's say, null string for seller, and then null for.
That's right. So of course, if you knew that, so the point that I'm trying to make here is that kind of this entropy, this Shannon entropy, does not give you enough information to use my box safely. Because in particular, you don't know which is this kind of special string. Because you so you don't know what's going on inside my box, okay? So my box is doing this. But the only promise that I'm going to give you is that it has entropy roughly n-half. That's all that you know about my box. Okay, I could pick any. In fact, my argument would work for putting any of these strings here. In fact, I might pick one at random and then prepare the box, putting the random string here. Okay. I, of course, know which one it is. Okay. 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 So somehow this entropy seems kind of very cool. I guess maybe you've already encountered it somewhere else. But it doesn't seem to be a very satisfying measure to tell us something about how random this box is, or kind of when can we use this box, or kind of how can we produce random bits from this box. Because it's very large. Like if n is like 1 million, this is like 500,000. It's pretty large, not so bad. But yet, kind of the outcome you would say is not very random because I can guess it with probability half. So this is why I very much liked your suggestion earlier, okay? It's because you said, well, maybe it has something to do with how well I can guess this x. And kind of in my distribution, kind of one of the outcomes occurred with probability half. What mattered is actually not kind of some average of these probabilities. I know I may have many of them. I don't know what they're doing. Actually, in my example, all the other ones are super tiny. But what mattered is kind of the largest peak. So the largest peak in the distribution is precisely given by what's called the min entropy. Okay, so the min entropy of some string x is minus the log of the maximum of all these boxes. So can someone tell me what is the min entropy for my example box? Huh? It's not, well, okay. Could it be 0? Okay, let's think about this. So in my example, kind of here's a 1. Okay. My largest peak in my distribution is a half. Okay. Yes? Okay. So in my example, in fact, the min entropy of x was 1. Okay. In particular, it remains constant and is independent of the string a. Okay. Okay. So here we talked about the min entropy of some distribution, but I guess we're later going to do crypto, and kind of we're interested in kind of what is the distribution given some knowledge that I might already have. So classically, some information that I might already have is just some bit string. Okay? Like I can open my book, I don't know, I can read, and then I'm interested in what is the distribution over x given this extra information. So let's say that you actually have some classical information E about the string x. And crypto people like to call this also side information. Okay. So given this kind of classical side information E, the min entropy, so this is all purely classical still, okay, just classical distributions, is given the minus the log of the sum over all the possible symbols that E could be taking, the probability that they occur, and then the maximum over x for that particular E. Okay, so I'm interested in the probability that conditioned that I have a certain amount of information, certain kind of information, like a particular page, what is the distribution of x. Okay, so this can also be written as minus the log. Okay, so here we write x given e. So this is some notation that kind of people like to employ. Let me maybe write this clearly. Okay, so this just means that I'm looking at the min entropy of x, given that the side information e takes a particular value, little e. Okay. Okay. So note that this also just means that we're going to make a guess. Okay, it means that we're always going to guess the most likely x, given the e, the side information that we have. So I guess we want to do quantum. Okay. And in kind of the quantum world, like tomorrow, we might produce a key, in fact. This kind of side information E might not be kind of classical, but it might be some quantum side information. Okay, so what is meant by that? So it means that this state, rho xe, is of the following form, namely there's some distribution over classical symbols x. Okay, I don't know how I've generated them. Okay. And then depending on this classical string x, E might have some information, some quantum state that somehow encodes some information about x. Okay. So people have kind of a name for this. People also often call it a CQ state to remind themselves what is kind of the classical and what is the quantum system. So this is kind of the C part, and this is the Q part. So can someone maybe make a speculate how we're going to kind of write the min entropy of x given E if E is actually quantum? Yes, you want to speculate?
Probably just the sum of the entropies.
Okay. So which entropies of what am I going to sum up?
So the entropy of the classical distribution and the entropy of the random distribution.
I could try that. But let's maybe, to get some inspiration, let's look at kind of how actually the min entropy was used in the classical case. Okay. So kind of classically, we saw that this entropy tells us something about how well we can guess x. So suggestions for how am I going to write the quantum min entropy, so to say? Actually, can you read the red? This is good. Okay. What am I going to write there? Yes?
Well, maybe minus log of maximum of overall Q states of the Q states of the matrix elements of this Q state in the density matrix. So bra Q states and then the density matrix and then S Q state. Okay,
so you mean that I actually decompose this one into pure states?
No, I mean that I maximize over all possible projective measurements, and every projective measurement will give me a probability of getting some result, and then I choose the maximum probability. So.
Okay, so this is a very good idea, even though I guess they don't necessarily have to be projectors. Like, if we take kind of this idea of trying to guess x to its kind of conclusion, you could imagine that kind of depending on x, we have a certain quantum state. And what we want to do is we want to distinguish them. Okay? So we're going to make a measurement with some outcomes, which I label x. So we make a measurement. Actually, let me make some space here, so I don't need this. So given this, I might consider maximizing over all measurements the following quantity. So with probability P of x, we're given a state rho x, and we want to find a measurement that distinguishes them. Okay? So a measurement is described by some measurement operators, and I label them mx. Okay? Because if I get this measurement outcome, then I'm going to guess x. And then in this case, this is the probability that given the state rho x, I give the right answer, okay, using this measurement. So you had suggested we should use projective measurements. Actually, we don't have to do that. In fact, there are situations where we don't want to have this be a projective measurement. Okay, let me say that. So we're going to maximize over all measurement operators. So this can be a P of m. Okay, so we know that, I write it at the bottom. So all of these operators are positive semi-definite. And if I sum them all up, if I sum up over all the possible outcomes, then I get the identity. So, but note that this does not have to be a projective measurement, even though projective measurements, of course, satisfy this property. Okay. Yes?
So there are several probabilities Px of the state Pex happening. Isn't that already included in that information? That's very important.
Yeah, so note that I have here normalized them. So you can think that one way to generate such a state is, okay, I'm going to actually toss a coin. I'm going to produce n bits according to some probability distribution, P of x. And then I'm going to send to you a state rho x.
But for me, that should be, the density matrix already includes classical values, so it's like probability of probabilities.
No. So note that the overall state is described by this, okay?
Okay.
Yeah. So your goal is to figure out what is this x, okay? Depending on the state that you have. So with probability P of x, I give you a particular state. And then this is the probability that if you had this state, you will give the correct answer. So this is the average probability, average probability of being correct, averaged over the choice of strings x. Does that answer your question?
I think I didn't understand the setup.
Okay. Is it clear now?
I guess.
Do you maximize over all possible measurements, right?
That's right, yeah. So we're trying to find the very best one.
And then, in principle, apply this measurement to get, let's say, the best probabilistic result. Right?
That's right.
Okay.
In fact, if you think about all the way to the beginning of our lecture, you already saw an example of this. Namely, I had asked you, I give you either the real state or the ideal state, and you want to distinguish them. Okay? You make a measurement that is two outcomes, real or ideal. If I get real, I'm going to guess my state was real. If I'm going to see ideal, then I'm going to say it was the real ideal state. Okay? So you can think that this is just a slightly more general scenario, where with some probability Px, like you don't know the string, I choose a string with probability Px, and then I'm going to send a state rho x to you. And your goal is to figure out what was x, given this quantum state.
And Px is known, right? Distribution is known.
That's right, yeah. That's a good point, okay? Distribution is known. In fact, if you want to find the optimal measurement, you know the distribution as well as the states. Okay. So note that what we did classically is really just exactly the same thing. Okay? So classically, I had said, okay, we're trying to guess x given the information that we have. We have some information E, some classical string, a page in a book, and given E, I'm going to guess the most likely x. in fact, I can encourage you, if you want to do this kind of as an exercise, to take this, plug in kind of classical distributions, so states which are all diagonal in the same basis, and then see whether you can kind of recover this classical expression for the min entropy from this. So the upshot of this quantum min entropy is that it's really the probability that given E, I can guess X. And this guessing probability, if you want to be smart about it, is exactly kind of the maximization of all possible measurements that kind of might tell me what is X. So it turns out that this quantity can also be defined if this is actually not the CQ state, but it's kind of QQ, like quantum and quantum. But maybe I won't do this yet, but you can ask me in the break, and then I'll answer all your questions about that. Okay. So what I want to kind of talk about now are some very elementary properties of this quantity in red. Okay. Yeah, let me use this one, because otherwise it's very difficult to read, I find. If it tries. Okay. So what are some properties of this quantity? And I'm not going to prove them formally, but I'm going to appeal to your intuition to kind of see whether they're true. Okay? So I'm going to claim that the min entropy of two strings x and y, given E, is larger than the min entropy of just x. And to kind of think about this, I maybe want to ask you a more simple question first, namely, what is the smallest and what is the largest value that this quantity can take? What is the smallest value?
Zero.
Yes, so the smallest value is 0. So when is it 0?
It's complete random.
Let's investigate this. Okay. So if x is classical and E is quantum, then indeed it turns out that this will always be positive. And my question to you is why? In particular, when will it be 0? So to think about this, let's remember kind of what this entropy actually is, okay? Namely, it's minus the log of the probability that I managed to guess x given E. So when is it 0?
We know the answer for sure.
Okay. So in this case, kind of, we know the answer. Like, if the probability that we guess is 1, okay? So this might in fact happen. Example of this could be, I take the string and I just send the string to you. Like, you know exactly what it is, okay? You can guess it with probability 1. Okay, so in this case, kind of the min entropy is exactly 0, okay? So this is attained, so it's equal if kind of we can guess perfectly, okay? So the guessing probability is 1. So if I have an n-bit string, what is the maximum that this quantity can take? N, okay. So when is it n? Yes?
It's again uniform.
Okay, very good. So if it's uniform, meaning that, well, in fact, x is uniform and uncorrelated from E. Look, I don't know anything. The best you can do about some kind of coin that I'm going to produce is you can make a random guess. I'm going to be right with probability 1 over 2 to the n, because there's 2 to the n possible strings. because we take the log of that, that gives you n. Okay, so this is the case where the probability of guessing is just 1 to the n. So given that we have kind of this quantity is very intuitive in the sense it tells us something about guessing x, I wanted to ask you whether you have some idea whether this might be true. Okay, so this is the min entropy of two strings, x and y, and I claim that it's larger than the min entropy of just x. Any ideas? Yes?
Well, if you know why exactly, so like contain E, then it's just the same.
Okay, very good. Okay, so like there's a condition here when these are the same. Okay, namely, for example, if kind of E is just like knows y, okay, then they're the same. So why is it larger actually?
Well, why might be unknown.
Okay. So note that if we kind of think that this quantity tells us something about guessing, okay, so note that this quantity is larger if it's more difficult to guess, okay, and it becomes smaller if it's easier to guess. Okay. So kind of guessing two things classically is kind of more difficult than guessing just x alone. Okay. So you can check this if you want. So there's one more important property that I want to establish, and this I'm not going to prove, even though I have some very bad news for you. Namely, I'm going to ask you to prove it for the classical case in my exercises. Okay. So I'm claiming that the min entropy of some string x given E is always at least as large as the min entropy of x minus the logarithm of the number of kind of the size of E. So this is the dimension of the system E. Okay? So I guess you can also call it dE. This is dimension of E. And I'm not going to prove this here, but I'll give you some intuition that some relation like this should maybe be true. So what this says is that kind of if E is very small, okay, say it's just one page, but it's not an entire book. Okay? If I give you just the amount of information that fits on one page, and you're trying to guess an entire book, X, which is much larger than this one page, then you can kind of think that the amount, or like the advantage that I get by having this page is never larger, is never larger than by, or like the min entropy is never reduced by more than kind of the size of the amount of information that could possibly fit on this page. So how are we going actually? I've kind of lost track. Any takers? Did anybody keep track? No? Okay, that's good. Or not? Okay. Great. Okay. So what I want...
The same some relation if we separate two quantum systems into two. As you make like x, y, and we have the same for E1, E2. Something similar, please?
So there are bounds known, but it's not precisely the same. But I can show you in the break. Yeah. Okay, so what I want to do now is I want to kind of produce kind of very good randomness, or something which is at least close to our beautiful ideal world, starting out with something that is somewhat crappy, like my box, for example, okay, or boxes of this kind, about which I have only minimal guarantees. So let me maybe write this here. Okay, so we kind of want to remember that the mean entropy So let's say that we're going to produce a box, like my crappy one, that tries to produce some random numbers. Okay? It outputs a string, x1 up to xn. But let's say that this string is not perfectly random. Okay? It does not satisfy this condition, but maybe it is somewhat random. Okay. In particular, maybe we know something about the mean entropy, or maybe we have even some stronger guarantees. And so the goal of what is called a randomness extractor is to turn some kind of semi-crappy randomness into something that is very close to ideal. Okay. So randomness extraction is sometimes also called privacy amplification in QKD. For reasons that I guess we'll see tomorrow. But it exists actually quite independently, and if you're kind of curious about these things, it also has some beautiful relations to the theory of error correction classically. And there's a lot known about this kind of procedure classically. So what is a randomness extractor? Okay. I'm going to write this as a function. So x is some function that takes my strings. So it's a mapping from kind of n-bit strings to m-bit strings. And typically, kind of, if I start with n, which is sort of semi-crappy, the number of kind of bits that I will extract is much smaller than n. Okay. Can someone maybe tell me why m should be smaller than n? Could I be trying to hope to get something that is kind of more randomness, like a longer m from kind of a shorter n? Yes?
The distribution of the n random numbers is not perfect. I can, for example, by adding them up, get something smaller.
You mean you want to make it smaller or larger?
Smaller.
Smaller.
Okay. If I extract less random numbers, they are more uniformly distributed the old ones.
Okay. Okay, so very good. It's definitely possible to do some instruction to make it smaller. Did you want to say something?
No, I just wanted to say that if you take this as an information measure, I mean, you can never get more information, right? So you have the same entropy, but then mapped onto less bits. I think that's what you were saying, right?
Mm-hmm.
So it's,
Finally, it's thermodynamical because entropy is not small. Yeah, unlike you get more randomness when you have more possible random states. It's why your entropy, I think it's more
Okay, I like all of these ideas. Let's kind of see how or when, in fact, such randomness extraction is possible. And I mean, it's somewhat important to understand this if you later want to go out and you want to buy a random number generator to use in your experiment, or maybe you kind of want to build one yourself. The question is kind of, what are the guarantees that you want to have on this x? Maybe you cannot make perfect random numbers such that you can find such an extractor. Okay. So I don't have time to kind of go too much into the theory of randomness. I'm just going to tell you when this is possible, and then I'll tell you when it's not possible. So if we want to build kind of extract random numbers from this, the question is, how much do we know about the source? So this means, how much do we know about the distribution, the probability distribution, by which these strings are produced? So kind of a very simple process is that I take a coin, And maybe it's not quite 50-50, maybe it's like 60-40. Actually, I haven't tested them, but maybe they're 60-40. But I flip it many times, and the process is independent. Okay, so this is called an IID source. Okay, so IID stands for independently and identically distributed. And it just means that each bit is chosen with the same probability and independently of all the other bits. Okay, so this kind of means that the distribution of like, I don't know, x is just some product of like x1, x2, x3. Okay. So for these sources, it is known that kind of randomness can be obtained. For example, using the von Neumann extractor. Actually, there's quite a number of possible methods to do this. And I kind of encourage you to look this up. Kind of a weaker form of this, in fact, which also allows you to extract randomness, is a source in which the distribution is not identical, but still independent. Okay? And if I know there's some distribution, like I have some probability for the first bit, probability for the second bit, and some other probability for the nth bit. Okay, so I'm using this notation not to take the power, of course, of this quantity, but to just indicate that these are different distributions. So in these cases, it's actually possible to find such a function that extracts random bits. Okay. And what I want to do now is I want to show you that in general, in fact, it is not possible to find a function that kind of takes my n bits and produces some random bits if I don't know enough about the source. And what do I know about the source? I'm again going to give you a very minimal condition. Namely, all I'm going to tell you is something about the min entropy of the source. And I'm going to tell you that it's at least k. Okay. So again, remember that these are kind of, this is the only guarantee in this case that I'm going to give you. You can think about it abstractly, like you don't know what's going on inside precisely. You have just somehow gained some confidence that this has min entropy at least k, and this is called a k source. Note that actually most kind of physical devices that you might want to build to kind of produce random numbers do have some kind of memory effects. Okay? And if you have some kind of memory effect, then it will typically not be an IID source and also not an independent bit source, because the probability of the next bit depends on the previous one. So people have also quantified this using some kind of Santa-Vasirani source from which one cannot extract. But I guess it's actually more easy to see that kind of if I just tell you something about the min entropy, then I cannot extract from the source. And I actually want to be somewhat adventurous, and I want to tell you why not. So I'm going to claim, in fact, if we have an n-bit string, and I'm going to kind of make this very special, I'm going to show to you that even if I have an n-bit string that has n minus 1 bits of min entropy, and remember that kind of the maximum that this quantity could take is actually n, right? So it has almost as much min entropy as it could possibly be having, minus 1. And my claim is that even though I have almost maximal min entropy, there is not a single bit that I can extract from the source. So even though this is true, we cannot extract even a single bit. to understand this, and I will show you this shortly, it is important to kind of understand that if you say I'm going to construct a source and all I know is something about its min entropy, then the source or the distribution over these possible strings can also depend on the extraction procedure that you're going to perform. Okay? Like you tell me, I'm going to, I don't know, XOR all the bits together. This is my extractor. Then I get to produce a source. My challenge is to kind of produce a source. I'm going to come up with a probability distribution that has that much min entropy, but I can perfectly predict the outcome. It will not look random to me. So my question is kind of how are we going to come up with this distribution? And for this, I want to define a set. I'm going to call it S0, which is the set of all possible strings, I don't know, such that if I apply the extractor to the string, then the outcome will be 0. Okay? And I'm going to define the set S1 to be the set of all the strings such that the extractor actually gives me answer 1. I can just define these sets. Yes? Did you want to ask something? Or am I just standing in your way again? Okay. Okay. So let me define these two sets. So let's make an observation. Okay, we have 2 to the n possible strings. And well, for every string, either the outcome is 0 or the outcome is 1. Okay? Has to be either one. There's no only kind of 2 options. My extractor is trying to produce a single bit, either 0 or 1. So this means that kind of if I add them up, well, every string has to be somewhere, okay? Because my extractor kind of tries to produce a single bit. So it's either 0 or either 1, so either string is here. So what this means is that there exists some bit, okay? So there exists one of these two sets that has at least half of the elements, okay? Because otherwise they couldn't add up to 2 to the n. So this means that at least one of the sets has half of the strings in them. Do you agree? So let me now consider the set that contains at least half the strings. And what I'm going to do, and I hope it's not confusing, is I'm going to make the set a little smaller. I go to a set S hat that has exactly that many strings. Okay, I'm just going to throw all the other ones away. Okay, I can certainly do that. And I define a set of strings. Actually, let me create some more space down here. So note that my goal is to defeat this extraction procedure. I want to come up with a distribution that has that much min entropy, yet I can perfectly predict the outcome. Any suggestion what this distribution might be? Yes?
Well, we can just take the set and one bit fix it, and we're done.
What do you mean by append the set to?
What I mean is we take the set of bit strings and just add a 0 onto in the last place into all of these.
Mm-hmm. You mean the ones in here? Or?
Yes, we take all these bit strings and just add one bit, because these bit strings are length to n-1. So we add one bit, so we have a set of bit strings of length n.
Okay, let's be careful. Okay, let's be careful. Let's wait. Let's backtrack a little bit. So my source is producing a string of length n. Okay. However, it has min entropy only n-1. Okay, so this does not mean that I'm kind of shrinking the string. It just means that the entropy of this n-bit string is not quite maximum. If it would be maximum, it would be n. But I don't quite have that. I only have n-1. So my challenge to you was kind of to come up with a distribution, p of x. Okay, your challenge to you is come up with a distribution p of x such that the min entropy is n minus 1. And yet, I can perfectly predict what's going to happen, yes?
You would say all random numbers that can be generated out of this set.
Okay, very good. Okay, so I'm going to choose my distribution such that if x is in this kind of magical set, okay, then, well, I'm going to kind of say, okay, it is uniform, but on this set. Okay. Okay. And if it's not in this set, well, I mean, then it does not occur. Okay. So how much min entropy does this source have? So if I compute the min entropy of that, let me maybe remind you again. In fact, this is all just classical. So what is the min entropy of this distribution? Huh? Okay, very good. N minus 1. Huh? Okay, we have made a distribution that has n minus 1 bits of min entropy. But yet, kind of, what is the outcome that you would guess? Like if I... Actually, my notation is mildly horrible. Let me kind of use this, call this as tilde. Okay. So what is going to be your guess? Okay, indeed. So like, let's say that the kind of the bit that had the more elements in it is, I don't know, 0. Okay. Then I'm going to guess 0. And note that my function is constant on this set. Okay. So note that for all the strings that could possibly occur now, okay, for all the strings that have non-zero probability, we know exactly the output of this extraction function. Okay. Because we know that for all of these strings that have this property, we also know that if I apply this extractor to such a string, then the outcome is going to be my x tilde. So I hope I've convinced you that kind of the guarantees that we need to have about a source if I want to produce random number from the source are actually somewhat non-trivial. Okay? If I have an independent bit source, if I have an IID source, then we can produce random numbers. If I have only very weak guarantees about the source, I only know the min entropy, then we have, in fact, we don't know enough to perform randomness extraction. Yes?
Able to identify such a defect or in the generator by making spectral tests?
Okay, so of course you can kind of say, I'm going to test my random device. I'm going to establish some extra criteria so that I'm going to learn more about the device than just its min entropy. Of course. So this is all this is saying, okay? It just means that just knowing the min entropy does not help you. This one. So things looked a little bit bleak, okay? Like I have the source, cannot make any randomness out of it if I only know the min entropy. But you've maybe possibly been to some quantum information talks before, and people in quantum crypto like to obsess over the min entropy, okay? So maybe you're wondering like, well, you know, if this min entropy is not good for extracting some random bits, why should we worry about it? Why have I been torturing you for kind of the past hour with this crazy quantity if we cannot use it to say something about how many random numbers come out? Okay. So the point is that, in fact, if we do randomness extraction, instead of using a fixed function, I might invest some randomness to kind of choose a function. So you can kind of think that what we're going to do is what is called seeded extraction. Namely, we're going to have the string x. Okay. So this is some imperfect randomness. In fact, the only thing that I want to assume is that we know it's min entropy. Okay, so I'm going to omit E, but the argument is identical. Okay, I'm going to say I only know it's min entropy. Not very strong guarantee. But I give you something extra. And what extra did I give you is I give you a random seed, okay, which I will call S. And the seed I will give you is, in fact, chosen uniformly at random. Actually, it doesn't have to be. But here I will choose it uniformly at random. Okay. And what we're now going to do is we're going to extract from both things together. So a seeded extractor is nothing else than a function that kind of takes our original bit string plus the seed, and from this tries to produce something which looks random to us. Okay. And to give you some intuition why something strategy like this might work, if you think back about our kind of construction or kind of Q construction, where we had n-1 bits of min entropy, but we could predict the outcome perfectly, we had tailored this distribution to this function. I tell you what this function was. We had made these two sets. We know it's kind of 0 on these strings and 1 on the others. And you could exploit this to kind of come up with a distribution that has large min entropy, but yet you can know the outcome is constant. You know precisely what's going to happen. So you can kind of think that using a seed, some extra randomness, we can avoid this. So you can think that what the seed actually does is that kind of instead of just using one extractor function, okay, so this is some function from the string, we're going to in fact have a few of them. Okay, so there's a few seeds, I don't know, S here, and there's some other function, I don't know, S hat, oops, S hat. And what I'm going to do is I'm going to pick one of these functions randomly. This costs me some randomness. I have the random seed, so I can make this random choice. And this way I can kind of thwart this, because basically, yes?
Do we know the set of functions? Because then I don't see the point to just don't use S. Because you could always say, okay, I'm going to defeat one of these functions. Mm-hmm. And if I know the set of functions, then that's equivalent to just guessing S. So we don't gain that much if we extract.
Indeed. So it's kind of cool that it's nevertheless possible. But you're kind of already getting at something which is quite important, because you're kind of worried if, for example, the seed might be very small. Okay? So basically, kind of what he's saying, and this is a very good point, is that if we kind of want to have any hope of doing this, we have to invest quite a bit of randomness, because if there's just two functions, maybe I can still kind of thwart them. Yes? Did you want to ask something?
So the point was that we don't gain any security in using the extraction in opposite to using the seed directly at a random number.
Okay, so this is also another very good point, because you are now asking fairly enough. Well, it's not so surprising that some randomness comes out, because after all, I had started with some perfectly random seed. Okay? So the goal of randomness extraction is to kind of produce more random numbers, so to say, than we started with. Okay? And I want to kind of tell you what this actually says. Okay. So we will be interested in what's called a strong extractor. Okay. Namely, it should have the property, like we want to get close to kind of our ideal scenario. So what should this extractor do? So the outcome, I'll write x of x. Okay, so it should have the property that whatever outcome I'm producing, so I'm applying my function x to the string, depending on, actually let me use a different color for that, the seed S, and possible some other information that the adversary already had, or like that E already has. So our goal will produce something that kind of looks random. Okay, so on the M output bits. And that is uncorrelated both from E and also from S. So our goal will be to find a set of functions such that even if I tell you the seed, okay, so I'm going to pick a function at random, I'm going to apply it to my x, then I'm going to tell you which functions I've applied, okay, so I'm going to tell you what is s. I want that nevertheless, the outcome that I've produced looks almost, up to this epsilon, random to you. Okay. I think it's amazing that this is possible. Yes? I see, okay. So there's now some, of course, very interesting questions, because you're like looking in disbelief how we might ever be able to find such a set of functions and how much randomness can we get out. So I'm claiming, in fact, that the number of random bits that we can get out is never larger than the amount of min entropy that we started with. Okay? So I'm claiming that kind of the number of bits that come out is never larger than this min entropy that we started with. Okay. And in order to think about this, let's maybe think about what we know about this x. Okay, so the min entropy is all about guessing x. After I applied this extractor, in fact, if I tell you what is s, okay, you might try and guess the output. Okay, so we know that, like, we might think about the probability of guessing the output of this extraction process. Okay, like I know s. Okay, I want to guess this. And I might think about the probability of guessing the output of this extractor given that I know x. So note that one strategy that I could guess the output of this extraction process is that I first guess x. Maybe not a good strategy, but let's say I first guess x. And then afterwards, I'm just going to apply this extraction function myself. Okay, so that would certainly be one way for me to make a guess for the output. Maybe not a very good way, but not so bad. Okay. So this means that the probability that I guess x, okay, given that I know the extractor function, is at least as large as the probability that I guess just x by this strategy. So remembering that kind of the min entropy just puts here a minus the log, we basically just reverse this inequality, and it says that the min entropy of this output can never be larger than the min entropy of what we started with. Okay, so I just get this by here, by putting here minus and log, and minus log. Okay, and then I reverse the inequality. So because this was kind of just k, I had promised you something about this min entropy, okay, we know that kind of the amount of random bits that we can extract is not larger than this min entropy. So this establishes this, okay, so this number of output bits. So maybe I'm trying to convince you, or starting to convince you, that the min entropy is not completely pointless, because at least it establishes some upper bound on the maximum amount of random bits that we could possibly get out. Okay. Yes, great. Indeed, you're shrugging, like, what is this? Like, fine. Okay. But you are still not believing that, in fact, we could ever do this. So whereas this direction was quite trivial, the converse direction is actually difficult. Okay? At least quantumly, it's somewhat more difficult. So it is known that, in fact, there also exists function for which the output can be exactly equal to the min entropy. And because we're kind of nearing the end of this lecture, I just want to state to you what such a statement is. And then we can use this for something interesting tomorrow. No, it's not so bad that we have a small whiteboard. At least we can all relax for a few minutes before we continue. Okay. Indeed. So unfortunately, like I said, my time is limited, so I cannot say too much about these functions. But I just want to kind of give you a set of possible functions that have this property. In fact, it's going to be somewhat unsatisfying because I'm going to define it just a class of functions, and then I'm going to claim that such class of functions exist. So remember what we were doing is that we're going to use our seed to kind of pick a function from some set. Okay? So my goal will be to say, what is this set of functions? So there is a set of functions, okay? So this is a set, and all of members of the set are functions from n bits to m bits. And I'm going to choose the seed to pick one. So a set of function is called 2 universal. So f is 2 universal if the following holds. Okay? Namely, for every possible strings which are not the same, the probability kind of that if I choose a random function, I get a collision in the sense that it maps both strings to the same value is small. Okay? And it's smaller in something that is related to the output length, namely it's smaller than 2 to the m. So this just says when a set of function is 2 universal, and I promised that I would be very unsatisfying because of this you might not immediately infer what this set of function actually is. So one set of functions, and this is also very unsatisfying, would be the set of all functions, okay? From n bits to m bits. Another set of functions is the set of functions where I choose some bits at random, like I choose a subset of the bits, and I XOR them together. This would only give me one bit out, okay? But that would also be such a set. So constructions for these kind of functions do exist, and unfortunately, of course, we don't have time to discuss them. But for 2 universal hash functions, the following statement is known. And I first want to give you the classical statement because this has been known for a very long time. And because I always misspell names, I have to look this up. And this applies if E is classical. Okay, so everything is classical. Okay. So they proved something which is known as the leftover hash lemma. And it says the following, namely it says that if I choose a function from kind of a 2 universal set of functions, then in fact I can extract m bits of min entropy, m bits of randomness, so to say, so my output is of size m, where m is equal to this min entropy that I started with, minus 2 times the log of the accuracy that I demand. Okay, so what is this funny epsilon? So remember that we had some kind of demands. Remember that we had some kind of demands, namely we wanted that kind of the randomness that we generate. Remember again, real and ideal. We wanted this to be smaller than epsilon. And it's somewhat clear that, of course, kind of the amount of randomness that we can get out should also have something to do with this demand, like what is our accuracy epsilon? If epsilon is 1, it's very large, we can perfectly distinguish the real and from ideal scenario. In fact, then we don't need to do anything. I can give you any state, and that will do. Okay. So the amount of kind of bits that we can get out using 2 universal hashing is precisely determined by this. Okay. So this is somewhat amazing, even though I guess you can see that these 2 universal hash functions might be very large. In fact, they are very large. Okay, so there's many, many functions in this set, which means that we need a lot of randomness to start with. Okay. But it forms a strong extractor in the sense that the output will be uniform and independent even from the seed. Okay, so even this the seed is not kind of put into the randomness on the output, but kind of the random output generated is uniform even given the seed. It's independent of the seed. Almost, okay, up to this epsilon. So we've seen that we can never get more than the number of min entropy bits out of the source. And what's very cool about their theorem is, the leftover hash lemma, is that in fact it's also possible to achieve this. So if we choose our functions randomly from the set of two universal hash functions, in fact any set of two universal hash functions, then we can also achieve that almost. Namely the number of bits that we can get out is equal to the min entropy minus the log of 1 over epsilon, where epsilon is this accuracy parameter. Yes?
That's actually independent of the length of the seed?
I see. So this is a very good point, like because you're asking, I guess basically, is it independent of the length of the seed? Or kind of how much randomness do I need to start with? Okay. So it turns out that kind of choosing F to be too universal is not very efficient in the sense that in fact these sets are extremely large. Okay. There exist other sets of functions, which I don't have the time to talk about, where in fact the seed is logarithmic in the input. Okay, so the number of bits here that I need in the seed is of order log n, where n is the input length. Okay. So this means that I have a long string, like n bits, and the seed length is just logarithmic in this. So these are quite very beautiful, in fact, and sophisticated classes of functions that you can sample from. And in fact, because I don't have time to talk about this, I encourage you to look at the survey on this. I'll put here some references for you if you want to learn more about this. Okay. So if you want to learn about the classical case, so kind of classical E, there's a lot known about the set of functions that can be used here. Okay? And kind of a very good survey is, for example, a kind of, in fact, like a lecture notes, a book by Salil Vadan. It's called Pseudo-randomness, but it's not just about pseudo-randomness, it's also about extractors. And there's also a book, a kind of survey by a guy called Schaltiel, which is called An Introduction to Randomness Extractors. Okay. So it's important to understand that these results hold for a classical E. Okay? So E is actually classical and not quantum. But it turns out, in fact, that the same can be done. And oops, if I have some kind of quantum E here, okay. And a good reference point for this, actually, which is very, I guess, hopefully accessible, is in fact Renato's thesis. You can also ask him. So you can also find this in some papers, but I think it's kind of easiest to write in his thesis, where it's kind of beautifully explained that in fact, using two universal hash functions, this also holds if E is quantum. Okay. So this would be, of course, very important for us tomorrow, because I guess if you want to do quantum key distribution, E will in fact be some information that the eavesdropper has gathered. Okay? So the eavesdropper can be quantum, and therefore might have a quantum state and not just some classical information E. So if you're curious about this, I want to give you one more reference about the quantum case, which is a very recent archive paper by Mario Berter and others, which has a lot of nice references in them. So I recommend this as kind of a source also for further references on the subject matter, because people have, there has been a huge amount of study. Like people have investigated all kinds of sets of functions that kind of allow us to extract, okay? But it's not a priori clear that all of these sets of functions still hold if I kind of have some quantum side information instead of classical side information. Okay. And kind of there's, in fact, by now much more known about this, and you can kind of read about this in this paper down here. Okay. So I'm already 5 minutes over time, so I won't torture you much longer. There's maybe just one important thing that I also want to say, and I just want to give you a reference for this. Because it can be quite important if you actually wanted to produce random numbers using some kind of physical device that you're going to produce. Okay. So if you make kind of a physical device that produces random numbers, you're maybe now disappointed. Maybe I cannot characterize my device very well. In fact, I might only know its min entropy. And I'm just telling you that the min entropy is not enough to extract. I'm telling you that you need this kind of magical seed that kind of falls from the sky, okay, and which allows us to choose a random function, and then we can extract. So in most kind of scenarios where you want to have random numbers, you will not have such a perfect seed, because where it's going to come from. Okay? So just the last kind of piece of information, or kind of just advertisement, you can go out and read some papers about it, that I want to make today is to say that, in fact, it's also possible in some relaxed conditions. So you can think that the scenario that we've constructed so far is we have a source that produces a string x, and what we know it is its min entropy. Okay? So we somehow established this. I don't know why, but somehow we know it. And I had told you that like we had required kind of a perfectly random seed S. So my seed S, and I had made a very strong demand, namely I had told you it must be perfectly uniform. So it turns out that one can relax this demand, and this is a much more realistic scenario. Let's say that you have another device, and I also know something about its min entropy. Okay? So this is actually a much more realistic scenario if you're trying to build a device that has kind of makes random numbers. And what I'm going to assume is that even though I just have weak guarantees here, like min entropy x, min entropy s, I'm going to assume that these are independent. And even though it might be very difficult to characterize some kind of physical device completely, okay, it's maybe not an unreasonable assumption to assume that if you have two devices, that they're probably going to be independent. You know, I'm a theorist. Naturally, they will be independent. If you do experiments, you might say, oh, they're connected to my same power source or something like this. Maybe not quite independent. That is true. But I suspect that kind of this is as close as possible as you can get to ensuring that these two devices are independent. So this basically means that even if I can produce some kind of crappy source of randomness, about which I can make a min entropy guarantee, if I have like multiple of them, in fact, possibly even more, then I can even still extract. And also there's kind of things known about this classically. There's quite a lot of things about this known classically. And there's a lot of work done by a guy called Yevgenis Dodis et al. Okay. And you can find references because people have recently tried to show that these procedures are still secure even if there's some kind of quantum attacker to this. And there's some nice reference in this paper here. So I can shamelessly advertise this. I think it's very nice. It's not my own paper. So this is where kind of people took these kind of classical multiple source randomness extractors and tried to make them proof against quantum adversaries. So there have been some limited work about this done before, and this paper kind of goes much further, and you can find all kinds of references in here. Okay. So I hope I convinced you that not all is hope is lost. We try kind of produce random numbers from kind of imperfect devices. So I hope you learned something, and tomorrow we'll kind of use some of these ideas to then produce not just random numbers in one location, but random numbers in several locations, like Alice and Bob, which will give us an encryption key. Okay, tomorrow.